5 minutes more on terahertz antenna, because within 1 hour it will not be possible to cover both the things. We worked for some time on fractal antennas, so let me start with this. Before I go there, I'll quote from Professor Prof. He says, with mankind's activities expanding into space, the need for antennas will grow to an unprecedented degree. Antenna will provide vital links to and from everything out there. The future of antennas reaches to the stars. 100 years from now, this is important, 100 years from now, in 2084, this statement he made in 1985, will our present technology, whatever antenna technology we have, will our present technology seem as primitive as this transmitter of Hertz now appears to us? So this was a statement made by Professor Krauss. Most of you are acquainted with that book, Handbook of Antenna by Krauss. So he made this in one of his seminal papers in AP propagation. So let us see what he predicted maybe after 20 years, whether that prediction is proving to be true or not. As you know, today, if you look at antennas, this is the common component in all wireless systems. And this is the only component that has existed for more than 100 years. That is why our community, antenna community, is special. It is the only, we are dealing with a component which has a history of 100 years. All other technologies, they have come, gone. The new technology has taken over, but antenna is there, it will be there. Now, if we are looking at mobile communication or wireless communication, new trends are something like this. Users are expecting more dynamics, more freedom, continuing stream of new applications like video, on move, capabilities and services. So all those things, they will require you multimedia applications. If you are going for multimedia application in mobile, you require antennas which has wide bandwidth, mostly ultra wideband antennas, which are very popular nowadays. Similarly, if you are need the multiple services or you want to be omnipresent, you require multi-band antennas. Now these demands are again growing, so that you require both the things. If you require multi-band, you require multimedia, you require wideband, as well as you require multiple frequency or multi-band. Similarly, for multiple services, you will require multi-frequency antennas as well as wideband antennas, because of if you remember this spread spectrum is also coming in a big way. Forget this, right? Okay. There are two properties, important properties for the antenna design for us. Most of the antenna engineers, we look at two things. One is what will the performance of the antenna, how the antenna is going to perform. So that is one consideration that we give when you are designing or analyzing an antenna. The second is what will the size of the antenna and what is the cost of the antenna. Whether you can afford it when it is going to the user, whether the user can afford the device which has this antenna, and what is the size of the antenna, whether if it is a mobile application, whether the user can move with the antenna. These are the considerations that we give into when we are designing antenna. Then based on these, we are dividing, classifying antennas. Beyond this, we also classify antenna based on two things. One is whether you have a mobile station, it is basically mobile antenna, wireless antenna, or whether it is the base station antenna. Both of them will have these characteristics. These are the characteristics which are common to both these. You should have good gain, high efficiency, ease of manufacturing, mean effective gain should be high, polarization diversity, if it is required, you have a diversity polarization antenna, easy to manufacture again. Then if you have a mobile station antenna like your mobile phone or laptop, there you require what will the Q factor, what will the bandwidth, whether it is conformal or not. If it is not conformal, it's difficult to put on your mobile phone. It should be lightweight, then ergonomic, should look nice, artistic, low cost, etc. For the base station, it is size is less restricted. You can have any size when you are using base station. Then other properties are there. Now, based on this, if you are asking one antenna designer or antenna engineer to design the antenna, he will have a dilemma if he is going to satisfy the user as well as the base station. The dilemma is this: the bandwidth and antenna size, they are inversely related, that we know, as well as we also know the antenna gain and the antenna size are directly related. So if you are going to increase the gain, you are going to increase the size. If you are going to increase the size, you are going to reduce the bandwidth. Otherwise, if you are going to increase the bandwidth, ultimately you are ending up decreasing the gain. So there he has to make some adjustment or some optimization where he will design the antenna properly for the required application. Now, what is the new trend in the antenna, multiband antenna or wideband antenna design? For that, let us pose this question to the audience, particularly to the young people. Considering the services which are provided in our wireless devices, how many antennas are required? But when I say services, which means you have audio service, you have video, you have data, you have multimedia, whatnot. So for different services, are you going to use different antennas? So for audio, one antenna; for video, one antenna; for data, one antenna; or you are going to use one structure which is going to give you service for all these services. So that is one question that will be in your mind. And all of them are at different frequencies. Audio is at different frequency, video is at different frequency. So that is something that you have to think when you are designing the antenna. So this is a new trend in when you are designing the antenna. The solution, if you look at the solution, for the solution we are going for fractal antenna. Now let us come to the topic. It is a fractal antenna. Why it is called fractal antenna and how it is going to give a solution, that we'll see in next few slides. But the solution is in fractal antennas. That is why the fractal antenna is important to the community. Now let us look at the concept of the fractal antenna. The concept of fractal antenna and arrays that results from two disjoint fields. One is your electromagnetics, other is fractal geometry. Geometry is a mathematics, completely mathematical field which has no relation with antenna, except we are looking at the structure of the antenna, that much is, and other is electromagnetic. So so there are two disjoint fields on which you are going to work if you are working on fractal antennas. Let us, so since it has two things, one is electromagnetics, let us forget the electromagnetics for the time being. Let us look at the geometry. We are saying that it is a fractal geometry. Geometry is a new type of geometry, so let us look at it first, then we'll go to the electromagnetics later. What is fractal? We define fractals as it is a recursively generated structure that has a fractional dimension. We'll see what is fractional dimension. And fractals also describe many real-world objects like mountains, leaves, such as clouds, etc. This term was coined by Mendelworth in 1975 for fractal geometry. Since then, this branch has been fascinating scientists in different branches of science, be it chemistry, be it physics, be it engineering. Everywhere people are fascinated by this. And fractal antennas and arrays, they have resulted from the amalgamation of two disjoint fields that we have said just now. Now let us say why I said that fractal. When you say fractal, it has a dimension, fractal dimension, fractional dimension. So let us look at what is dimension. Topologic dimension is, as you know, point has a dimension of 0, line is 1, it extends in one dimension. That is how you define how you are going to, what is the extension. If it extends in one direction, one dimensional line, extends in two direction, plane, extends in three directions, it is a cube, no extension, it is a point, 0 dimension. Then if you come to the fractal curves, as I described, these are different fractal structures. Fractal curves give you an infinite length. It's a line, but infinite length. So line means its dimension has to be 1. But that line, because of infinite length, that generates a surface. It is going to generate a surface. So it is neither 1 not 2, somewhere in between these two. So what will be its dimension? That we are going to see. Now for that, first let us define what is dimension. How you are defining dimension? Let us look at this. What is this? This is a line. Its dimension is 1. That we know. How do you define the line dimension? How do you know that its dimension is 1? Mathematically, how we are going to know that its dimension is 1? So let me take a box like this, which is, suppose this line is of unit length is 1. Let me take a box which looks like this and covers half of that. So box size is half the line. So if this is 1, box size is half. So I will require how many boxes to cover this line? 2. So I have 2 boxes. Using 2 boxes, I am covering the line. And delta is box size of the box, that is half. Number of boxes I required is 2. N is the number of boxes that I required, that is 2. N is a function of delta. Let me express N as a function of delta, where delta is the size of the box. You can take any N number of boxes. Here I am taking 2 boxes. You can take 3 boxes, 1/3 each. N boxes, 1/n each. Anything like that. So N, capital N, is the number of boxes that I am using, and delta is the size of the box. That is the box size. Now, total box are 2. This is 1 box. This is 1 box. This is the line. This is the line that I am going to find out its dimension. So total box are 2. So now I can relate this N delta, which is N as a number of boxes, as a function of the size of box. The number of boxes is 2. 2 I can write as 1/2 to the power half to the power minus 1. 1/2 is equal to delta. So I can write as delta to the power minus 1. So N delta can be written as delta to the power minus 1. Similarly, let us look at a plane. So plane can be formed by say 4 boxes. If I take 4 such boxes, I am forming a plane. Even if I take 2 boxes, I am forming it. No, so 2 boxes is line. 4 boxes, I am forming a plane. So for the plane, I require delta remains same, half, but N will be 4. So I am using 4 boxes. N is equal to 4. That I can write as 1/2 to the power minus 2. That is what is 4. For the delta to the power minus 2. Now let us look at a point. How many boxes I will require? I will look at only 1 box. Within 1 box, this point will be enclosed. So I will look at only 1 box. So N delta is equal to 1, which is 1/2 to the power minus 0. Now look at this. For the point, it is 0 to the power minus 0. For the plane, it is to the power minus 2. For the line, it is to the power minus 1. And we know earlier that for the line, the dimension is 1. For plane, dimension is 2. And for the point, dimension is 0. So somehow we are relating this. Dimension is related to this. Based on that, let us define the dimension. So since we are going to fractal, so I'll call it fractal dimension or the crippling factor. Crippling factor will be more appropriate than dimension to most of us. Most of us will be more comfortable with the crippling factor instead of dimension. So for that, what we do is we say that number of boxes N delta of linear size delta required to cover the geometry or geometrical structure that we have to find out first. Then the dimension of the geometry D is given or is related by this N delta is equal to delta to the power minus D that we have seen in the previous slide. Now if I take log of both the sides, I get log N delta is equal to minus D log delta. From that you can see or say D is equal to log of N delta upon log of 1 by delta. So dimension I can easily find out using this formula. If I know what is N delta and what is delta, using that or finding out how many numbers of boxes I am going to use and what is the size of the boxes or counting the number of boxes that covers the complete geometry, I can find out what will be delta. Now this can be a integral number, it may not be an integral number, which means dimension may be integral, dimension may not be integral. Based on that, let me come to the first fractal structure which is very common fractal structure. This is called a Koch curve. So how I generate that is I take a straight line of length L, then divide it into 3 parts, 3 equal parts. Take out the middle part, make it 4 equal parts, and from this straight line I come form this. This is called the fast iteration fractal. So what I have made basically is this length was L. Now if I come to this is L, then plus L by 3. So it remains same distance from here to here. That distance remains same. Over the same space, I have increased the length. Remember this. With the same space, you are increasing the length. So I have increased the length. Then I can go to the second iteration in which each one is a straight line. Here, this is a straight line. 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 With each one, I will do the same thing. So this will be like this. 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 Right. So this way, if I keep on iterating within the same space, I am going to increase the length. I will keep on increasing the length by iterating it number of times. This is what is called a Koch curve, or the structure is called a Koch fractal. Of course, here you can see what will be its dimension. Dimension will be 1.26. If you find out using the previous method, suppose I take a box which covers this one, so I take where this is 4 boxes for this one. For this one, I need 4 boxes. Number of boxes is 4 for one line. So then you can use it. Find out what will be the dimension. Dimension will be 1.26. Similarly, if I come to the other structure which is very popular, Sierpinski gasket. The upper one is called Sierpinski gasket. Lower one is called Sierpinski carpet. These two have this I can generate by take a triangle and take 1/3 of that out. So middle portion, this one I am taking out. This is the first generation. Then I have got 3 triangles. From one triangle I have got 3 triangles. Again, here I can use the next iteration. I can get 9 triangles. So this way you can keep on increasing. Similarly, here you have got a square. Take out the middle portion, 1/3 of that. So what I have got is here 8 squares. This is 1, 2, 3, 4, 5, 6, 7, 8. 8 squares now I have got. From one square I have generated 8 squares. Then here each 8 will be again, each one will be again 8. So 8 into 8, 64 squares. So that is what I am going to do for the carpet. So here you will get the dimension will be log 3 by 2, which is 1.58 for the Sierpinski gasket. For the carpet it will be 1.893. This you can calculate easily using the formal method. So this is a brief introduction to what is fractal, how you can find out the fractal dimension. If you have looked at those
geometries in 2D plane, how do you explain that physically someone is 1.58, someone is 1.8, something like that? How do you explain that?
I could not get your question. Yes.
That all what are the geometries are there? All in 2D plane. All the geometries, but
it can be in 3D plane also. You look at the sponge, that is 3D.
Assume that your the what structure
it is on the 2D plane. It is on the 2D.
Dimension is supposed to be 2. How you are getting me
that is why I showed you this one first. That is why I showed you this one first. This is how you are defining dimension. That is why I defined dimension. What is dimension? That is what I defined.
different from the conventional dimension?
No, that is not. It is not different from the conventional dimension. It is different only in the sense that you carry a concept that dimension can be integral only. It is not always integral. That is what I said. From the childhood you carry a concept that it can be only integral. That is why I define what is dimension. What you mean by dimension? When you say it is integral, because you from the childhood, if I say you that the dimension can be 1.58, a child will not be able to comprehend it. That is why from the childhood you know that 1 dimension, 2 dimension, 0 dimension, 3 dimension. But how you define dimension, how that has come? That has come this way. This is how the dimension has come. In the geometry, if you look at the mathematicians, you ask them, they say that dimension is defined like this. This is how they define dimension. Right. It is a concept. There are many wrong concepts that we carry out throughout our life. So conceptually, dimension is 1, 2, 3 dimensions for us. Like, how do you define n dimension? You know only 3 dimensions. How do you define n dimension? In physics, people deal with n dimensional things. How do you define that?
But in that case, in those cases, still n is considered usually as your integral multiple or integer.
Yes.
But in these cases, this fractional dimension is possible. That's what is interesting.
Yes, that is what I am saying. Dimension by definition, dimension is not restricted to only integral values. It can take any value.
The other thing is that if for any complicated geometry,
Mhm.
or some plane,
Mhm.
if dimension cannot be
It cannot exceed 2. It will be between 1 and 2. And you see these dimensions are not more than 2. Whatever dimension I am showing you, it is always 1 and between 1 and 2. It is approaching 2, but it is not never exceeding 2. It will never exceed 2. What I told you in that line also, it is going from 1 dimension towards 2 dimension. Whether dimension is 2 or dimension is 1, neither 1 nor 2. If you remember the geometries, what we are doing is we are doing two things in these geometries. We are doing two things. One is these geometries are self-similar. One is you can look at this triangle, triangle, triangle. You started with a triangle, but all these are triangles. Second is they are space filling. Like if you look at, it will be more clear here. You started with this, but you are filling up the space. If you look into this, this is filling up the space. So they have two properties. And these two properties, so fractal, when you say fractal, it has to have two properties. It is not only the similarity, it has to be two things. One is filling up the space, space filling, and self-similarity. These two properties are to be satisfied for the fractal antenna, and they give rise to, if you are looking at space filling, this gives rise to miniaturization. Over the same space you are increasing the length, so that gives rise to miniaturization. And self-similarity, one length, second length, each length is corresponding to different frequencies. That is why you are going to get multi-band. Then if you are intelligent enough, merge those bands, get broadband. If you want to get broadband, so that is where the concept is there. That is where your thing comes up. But as fractals, they can give you this. And this fractal, the term was introduced in an invited talk in IEEE seminar in 1993 for the antenna. In the antennas, this was by Werner, D.H. Werner. He introduced the fractal radiator. So for the first time in antenna, it was used in 1993. The term, I am not saying the antenna, I am saying the term fractal antenna or fractal radiator was used in 1993. Fractal geometry term was used in 75. So fractal geometry came in 75. People called it fractal geometry. It was existing earlier, but people called it fractal geometry in 75 and as antenna fractal radiator in 93. Let us go beyond this. Forget this, right? This is how many patents have been obtained by people. Now, let us look at whether there were fractal antennas, multiband antennas or broadband antennas pre-Werner era, which is before 1993, whether this was all existing or not, or Mandelbrot, whether this was existing or not. Most of you know that in the 1950s, spiral antennas were there, Lockheed antennas were there. They are also repeating, the same structure is being repeated, which means fractal antennas existed in 1950s also, but in a different form. And since the name or the fractal term was not coined as fractal, so people were not calling that as fractal antenna. It was given some different name. So they were existing before the term fractal came, or before the term fractal antenna came. These things were existing. These were in existence, and these were best. Uh, if anybody has read this frequency independent antennas, he knows about this. Victor Ramsey, frequency independent antenna, he has written a book on the research that has been done on these antennas, this type of antennas, and he says in that book that the impedance and pattern properties of an antenna will be frequency independent if the antenna shape is specified only in terms of angles. That is what he says there. That is the essence of his book, if you read his book. Now, what does that mean? That gives rise to Ramsey's principle that we follow. The principle is like this: the scalability of frequency independent antenna. How you are going to scale it, and its basis is actually Maxwell's equation. As if Antenna means it is all bases are Maxwell's equation. So this basis is also Maxwell's equation. But how? How Maxwell's equation? From the basis. Basis comes from this. Antenna becomes wavelength independent under a coordinate transformation. Like if you are having from x, y, z, transform to capital X is equal to x by lambda, y by lambda, z by lambda. So since you are normalizing with respect to wavelength, you are again the same functionality you will get in the electronics. So this is basically Ramsey's principle that we are going to use in fractal antennas. So up to now, if you have understood two things. One is fractal antennas are not new. They are basically frequency. They work on the principle of frequency independency. So that is one. Second is the dimension can be fractional. These are two things that you have understood. So now let us look at some of the important antennas or some of the early days antennas. One of them is the torch antenna. If you look at this, we are starting with zeroth iteration antenna, which is a dipole, normal dipole. Then this is the first, second, that way we are going up. Now for that, if you look at the input impedance here or the reactance part here, you will see that K0 is here, K1, K2, which means K0 corresponds to this one, K1 corresponds to the next one. So that is how. Now if you look at this, you will see one interesting thing. That these are, as you keep on increasing K0 to K5, these are going like this. And the bandwidth is actually narrowing, decreasing. So from that you can say with increasing iteration, as you keep on increasing the iteration, the radiation resistance is increasing and the Q factor is decreasing, and thereby it is approaching the Q's limit. Now let us look at, I'll look at Q's limit just one or two slides after this. So Q's limit, for Q's limit, you know what we do is we enclose the antenna within a sphere. So this is a sphere which is enclosing the antenna. The same sphere is enclosing this antenna also. That is how it is approaching the Q's limit. Now you know what is Q's limit. Q factor is given as 1 upon Ka to the power Q, or Q is equal to Ka to the power minus Q. K is the wave number we know, and A is the radius of the sphere that is enclosing your antenna. That is what is Q's limit. Now what does it do? It establishes that at resonance there is a relationship between the bandwidth and Q, and for large Q or for the smaller antennas, and we know that if Q is large, bandwidth will be small, Q is small, bandwidth will be large. Now, irrespective of the shape of the antenna, for the small antenna this is what it does. That means the efficiency of the small antenna depends on how well the radiator or the antenna is using the spherical volume within which it is enclosed. Now let us look at whether whatever has been told by Q, Wheeler, etc., whether that is true or false, or what is the validity of that Q's limit. And shall I take that everybody agrees here that Q's limit is valid always, all the time, for all antennas Q's limit will be valid, is valid? How many of you disagree to that? Yes, when it will be invalid? If you disagree, tell me when it will be invalid. If it is invalid, when it will be invalid? Question is, what is the validity of Q's limit? And to date, most of us will agree that Q's limit is valid, is a valid thing for all antennas. Whatever antennas you are designing, for everything Q's limit is valid. So if you are saying that you are disagreeing to that, give me one example where it is not valid or when it will not be valid. Okay, let me say that this, when you look at validity, it is valid only for simple TE or TM fields, for the antennas that are dealing with TE and TM fields. Now, what about compound fields where you have TE plus TM? If you require that, what happens there? And they are in right phase. What happens there? Whether Q's limit is valid there? No, it's not valid. It's not applicable. So what if it is not applicable? So what happens there? It is not applicable. If Q's limit is not valid, well, how it is going to affect me? The reason is it affects me in this way. it leaves open a complete field where I can build antennas and I can cross that limit. Q has fixed a limit that I can cross if I am going to design an antenna which has TE plus TM. For example, if you look, remember the spiral antennas or the sinus antenna, etc., or self-complementing antennas. You have both TE and TM there, and there you are crossing the Q's. There you can cross the Q's. And all those classical antennas that we are conversant with, those classical antennas are either for the TE antenna or TM mode, so their choose limit is valid. So for those antennas, you need not worry anything. So what we have to do is we have to look for antennas where both of these are existing, TE and TM are existing. So for this these antennas, classical antennas, we are not worried. So we are looking at a different type. Which one? No, it is in the antenna when you are designing inside the antenna, assuming that antenna is like a wave. Then there are certain other things that you can look into. The first one is Nathan Cohen. He worked on Minkowski fractal loop. This is what is called a fractal loop, Minkowski fractal loop. Numerically, he studied that and showed that a relatively high radiation resistance and low Q in factor can be existing for this antenna. So for the first time, he showed numerically, not with the experiment, numerically he showed that it is possible that you can exceed the Q's limit or you can cross the Q's limit. The second, here you can say that in a fractal shape, if there is a, look at this, how many places are there? All these places, all these bands are source of radiation. There will be acceleration, charge acceleration will be there, and you know acceleration of charge gives rise to radiation. So all those places are sources of radiation. From there you are going to get radiations. So that is what he says. Actually, Cohen started with this, and he has formed, later he has formed his own company or own industry. So in fractal shape, there are multitude of places along the antenna where the charges are strongly accelerated to produce radiation. It is possible, because of that, it is possible, possibly necessary to consider a two-wheeler limit, that you can cross the limit, because when you are looking at a dipole, you have two points where there is a change in acceleration, or acceleration is there at this end and this end. These are 2 points. Here you have got enough points. So based on those two, Q and Wheeler have formulated their theory. Now if you have got multiple things, the theory is to be recasted, or we have to work on those theories for the theory for this one. Second is Binay will come. Dr. Binay, when he was working at Penn University, they worked on this type of antenna, Hilbert curve antenna, which is also a fractal, Hilbert curve fractal antenna. They worked on this, and they concluded that third iteration has very good surface filling property, approaching a fractal dimension of this 1.834, and the higher the order of iteration of a fractal, the lower will be its resonant frequency, because the length keeps on increasing. Based on that, so since you are going to lower the resonant frequency, what is going to happen? Because of that, you can also look at the fundamental limits on the antennas, or the choose limit. So these are two things based on which we can look at crossing the choose limit if you are going to use fractal antennas. I'll say you why when I said TE plus TS, that we will see later, just after a couple of slides. This is the Quach antenna, for which Binay, etc., Vardhan Loop, they have given this formula. Now I am coming to the antennas that are existing. So up to now we have discussed about what is the background, or what is the basis of fractal antenna, how fractal antennas have succeeded, or how they are going to succeed. The only thing is there is no concrete theory for the antenna. Now you do not have a closed form formula for finding out the field, radiated field. You do not have a closed form formula for finding out the resonant frequency or impedance, etc. People are working on those aspects, and those are still open fields on which any of you can work. For this type of antenna, quad antenna, this is the resonant frequency that was proposed by K.J. Vinay and his group, Vardhan's group. Here also you can see that it is coming like this. And if you look at this, here the bandwidth will be large, here the bandwidth will decrease. The second antenna is a change of that. It is called a tree fractal. Here we are looking at trees. So what they do is they take a simple dipole and load it with tree fractals. Now doing this, it behaves as if the antenna dipole is loaded with this, and the impedance, loading impedance, you can keep on changing or varying here. Later, what they have done is, here they have put switches. So based on those switches, you can MEM switches, you can switch on or switch off some of the loading. So loading can be controlled later, depending on your application. So that is how they make it reconfigurable. With that, why you are going for loading? With the loading, they are reducing the size. Size gets reduced by about 40%, up to 40%. So somewhere 36 or 37%, up to 40% size reduction can be possible. Based on that, we had worked on the dipole antenna instead of normal dipole. We worked on the V-type dipole and found that the same properties are satisfied here, except one thing. And the thing is, I am taking a single iteration. First iteration. First iteration means I should get only 2 resonant peaks. Here I am getting 3 resonant peaks. That is the difference. I got 3 resonant peaks. This one, yes, this one is not good enough, so we rejected this. We used this too, but here we got 3 resonant peaks. That is something that we are working. Why we got this one? We have not got the answer to that. What is this? We have tried making the simulations also. The simulations also give this. We started with DDD, then we converted to IE3D, then also the same thing. I don't know why that has happened, but that is possible. Only thing that we took care is we looked at this current direction on both the arms, so that the current is not going to cancel out and give you or reduce your gain. So that was the only consideration that we are going to give design. When we are designing, that was the consideration that we are putting. Then this is another important antenna, which is the Sierpinski gasket antenna. I think after this one I will stop. This is another antenna. Here it is, as I have discussed what is the Sierpinski gasket. Here you can look at this. We started with this, the lower one. This one. This is iteration 0. Then 3 antenna, that is my iteration 1. Then this one is iteration 2, iteration 3, 4, and we have got iteration 5. So we have got 5 iterations. So for the first iteration, when n is equal to 1, which means when we have this, these are the characteristics of the antenna. And when we have 5 iterations, this is the characteristics of the antenna. Now let us see what happens when you go from iteration 1 to iteration n or iteration 5. What happens here? Look at this. Because of those iterations, you are getting 5 bands. So first one is 0th iteration. Let me leave that. Or first iteration, I am leaving that. So band 2, band 3, band 4, band 5. When you are in band 5, this is what is acting. These 3 are excited properly. If I zoom it, this portion I am zooming, that gives me this. So current excitation, these 3 are excited properly. Now look at this. These 3 are excited. Based on that, you are getting radiation pattern. Now when I come to band 4, the same thing is coming here. So this is what is excited. So zoom it, that gives me like this. So this is the first one. This is for the band 4. This is for this is for band 4. This is for band 3. This is for band 2. Now if you look at this, initially current is limited to this. Then current keeps on growing. It keeps on going to these parts. Based on that, what will happen if you are looking at a fractal antenna? This is going to invariably happen in your fractal antenna. This is going to give you a radiation field or radiation pattern which is completely different from this, and this one is going to give a different pattern. This gives you a flexibility or one advantage, that if you are going for different applications at different frequencies, you are going to use this, because everywhere you have a flexibility of using your own required fraction, your required pattern and frequency. That is at your hand if you are using fractal antenna. That is why fractal antennas became popular in the early part of 2000 to 2010. In that decade, it became popular because of this. Most of your mobile phones, if you are using mobile phones, they are using these antennas. Now let us look at what happens to the frequency. These are the frequencies. If you look at those frequencies, the lowest frequency is less prominent. If you are taking this, lowest frequency is less prominent and its bandwidth is lowest. Forget this. These are the patterns at different frequencies. Now look at the distribution of frequencies. They are almost log periodically distributed. They are distributed like log periodic antennas. So if you compare the log periodic antenna and the fractal antenna, log periodic antenna is expanding and this one is shrinking into this. So starting from this point, log periodic antenna expands like this. This one is sinking into itself, but using that space completely. Log periodic antenna requires more space. Here you have a given space, there you are using this. So that is the advantage of this antenna. Okay, this I have already told you. This shows the design of the same antenna. This shows the current distribution. Two things are there, or one thing is there to note, that in this design, if you mark this, this simulation, I am using here the field, coaxial field. Everywhere I have used a coaxial field. Why I am going to tell you later. But remember that I am using a coaxial field in great details. When we are simulating, my students, I ask them to use the coaxial field and use it properly. Definitely you have to use this. I'll tell you why that is required. Forget this. Let me forget this one also. This is a formula which were given by Puente and Peterson. They gave this formula when I was working at Birmingham. This formula we derived there with Peterson. This was by Puente for the same Sierpinski fractal, Sierpinski gasket. These are the regional frequency formulas. All these are empirical formulas. These are not derived. You cannot derive. We improved that those formulas. This is where we combine those two formulas. Are combined. First we combined them. Then we saw that there is mismatch with the experimental results. Then we improved those formulas. This one with this. This is published in AP magazine in the designer's notebook. So we improve that formula. That is one of our contribution. So then now this one is important by best. Now you see, if you are looking at these antennas, Sierpinski antennas, there are two things. One is a gap. These gaps are there. Then there are metallic filling are there. So these black portions are metals and white portions are gap. Now what is responsible for the antenna when it is radiating for the frequency? Which one is more important? Whether these black portions are important or these gaps are important? Which one is important? So to find out that, he did Stephen West. He did one experiment. First he closed everything except these gaps. These gaps are there, except that everything is closed. Okay. So is it from that he is trying to find out what happens. He sees like this is what happens to your S11 parameter. The return loss becomes like this. Then he starts filling these gaps also. Initially, first he filled these portions. Then he starts filling these gaps. So this gap is filled here. This gap is filled. This gap is filled. This gap is also filled. So pot out the gaps. Now what happens? So this is Sierpinski. This is Parani gasket, and finally he is modifying this. Now compare these two. Compare this one with this one. Now, can you tell me which is more important? Gap is important, or these metals are important? Comparing these two. Compare these two, this one and this one. If we compare them, then which one is more important? Which is affecting this antenna? Metal is important. Look at this and look at this. What is sorry? What is the S1 on here for this one, and what is the S1 on here for this one?
There it is around 25, here it is around 40.
40. So which is better? Where you have got better matching?
You are having less reflection here.
This is better.
Yeah.
So if you keep on closing this, we are going to get this in time. Now look at this. Let us close those gaps, center gaps, completely closed. We started closing them. We started closing the center gaps. From this, we got this one. Now let us completely close them, and only this will exist. Look at this. Now what happens? You said that if metallic is better, so we close them completely. Those are closed, except this. Now what happens? Compare this one with the previous one.
Here bandwidth is more return loss is reduced.
Bandwidth is more, return loss is reduced. Here, bandwidth is less, return loss is. Based on this, he concluded this. Resonance properties of the Sierpinski gasket fractal antenna is due to the central gaps. It is mostly led by central gap, not this side. Okay. Which means then we thought that what is happening is some sort of complementary antenna. Right. So based on that, instead of having a complementary antenna on one plane, we thought that let us try a complementary antenna on two planes. So this was the antenna that we designed. This is one plane, and above that we put the another one. This we designed, tested it. Only thing is, remember that both of them are fed. When I am feeding, this is not electromagnetically fed or passive feeding, active feeding. So the feed line comes to this, up to this, right up to this. So both of them are fed together. And that gives me something like this. Now if you look at this, what has happened here is this one has also become prominent. If you remember previous slides, this one was not prominent. Now using this, we have made this one prominent. They are prominent, these are prominent, this one is also prominent. Bandwidth has not increased that much, but reflection has increased, improved. Right. So using this one we have made prominent. So almost all bands are prominent now. Right. So that is something that we saw. Then on one plane we tried this type of complementary antenna. This also we tried. Here also we saw that this one is prominent. All of them are equally prominent. Okay, I'll take this. We design, what we do is we use the real coded genetic algorithm for design of these antennas, for fine tuning the things. So forget those things. Leave that. These are some other variants on the carpet antenna. Let me skip that. They exist. Just come to the terahertz part. Yeah, just skip this one or two slides. How much time I have? 5 minutes? Can I take 5 minutes? 10 minutes.
My question.
Huh?
The previous antenna shown filling up and complementary gaps.
Right.
Was it for the application of broadband antennas or multi-band antennas?
Multi-band antennas.
Not broadband.
No. That was actually by Stephen West. He worked on small antennas for multi-band application. He started with that. Then now people are working how to make them multi-band, broadband, because this by nature fractal antennas are multi-band. Now only thing is you have to optimize them so that the bands will be closer and you will get.
What will be the nature of comparison of that antenna? A simple triangular patch.
The pattern will be different. Current distribution will be different because current distribution will be different.
That means there was no gap at all. Completely filled patch.
If
Full gap.
no gap at all. No gap at all means you will get only one resonant peak. Only one resonance.
But it is tending towards UWB, single rectangular patch with sufficient optimized dimension.
Single rectangular patch with
Under biological mode, which will take the design from.
right.
It may tend towards ultraviolet band, not exactly from 3 volt but
No, there what happens is your radiation pattern remains consistent. Over the band radiation pattern does not change. Here you will get at different frequencies you are going to get different patterns. Patterns are different, so you have a multifunctional application. That this is one. So in one application you want this frequency or in this direction, other frequency I want this frequency, this direction. That is the application that you require for this one. This antenna will be used there. Not these are not used as UWB. They are not using them as UWB. It depends on what is your application. What is your application? These are all for multiband applications. All these antennas are for multiband applications. Now, how to decide on the geometry? The answer is when you choose or when you are going to choose a dipole antenna. For the dipole antenna, you can replace the dipole antenna with a cos. If you are going to use a triangular antenna, replace the triangular antenna with a Sierpinski gasket. If you are using a square antenna, square sort of thing, either square microstrip or a square monopole antenna, replace that with a carpet. So it depends the iteration zero geometry. What is your requirement? Based on that, design that geometry. From that you design. Then the chair has asked me to say something on terahertz antennas. We have one paper from our group will be on terahertz antennas. So I'm not going to tell you anything about terahertz antennas, but I'm going to tell you something else. If anybody is interested in terahertz, where he has to work and what are the precautions he has to take. I'll use only 2 or 3 slides. First is where is the terahertz, and second is at that frequency the attenuation is very high, atmospheric attenuation is very high, so you are not going to use terahertz for long distance communication when you are on the earth surface. Of course, when you are in space you can use terahertz antenna. There is no attenuation because once you go out of atmosphere, attenuation is out of question. So there you can use in satellite. That is one application. Other application is short distance communication, which we are using it in the space. Now, why you will go for terahertz? Answer is very simple. If you go to terahertz, compare with megahertz. 1% of megahertz, 1% of terahertz. That comes in megahertz. So when you require bandwidth, you go to terahertz. We will go to terahertz. And above that, terahertz is not licensed, unlicensed. So these are basically 2 major reasons why people are working or looking into terahertz technology. Problem is designing those things. Precision is very high. Precision is required. So that is the major problem if you are going to terahertz antenna. Even generation of terahertz itself is very costly. Somehow, suppose you generate terahertz and you are going to design antennas. What you will do? First is you will do a simulation. Most of us are going to do a simulation in this country. At least we are going to. First phase will be using a simulation. Now, when you are working at terahertz, the wavelength is very small. So, whatever design you are going to do, if you are using a dielectric substrate on which will support your antenna, if you are designing an antenna or any device, that will be on a dielectric substrate. Usually, you will take a substrate the molecular dimension or the atomic dimension or atomic size of that substrate and the wavelength will be almost same. They will be comparable. In that case, there will be problem. I am going to discuss what problems are there. Forget the first is you are going to use something, some physical dimension. Now the physical length will be very large compared to the electrical length. Wavelength will be so small that the total length of the substrate will be large. When you are going to simulate, you will require many meshes. Number of meshes will keep on increasing. Now, number of meshes is going to increase means you are requiring more computational time. That is number one. Now, when you are increasing number of meshes, there also you are increasing approximation. Each mesh gives you some approximated value. Result from mesh comes because of some approximated value, numerical approximation. So there will be some numerical error associated with each mesh. Now if you keep on increasing the number of mesh, the error is also going to increase. So ultimately whatever you are going to get, net result will have more error because of many number of meshes. That is, if you remember this Simpson's rule, integration, Simpson's rule of integration. Most of you have read that numerical method, Simpson's rule of integration. There, if you are going to increase the number of steps, step size, your result will increase up to a point, then it will start decreasing. The accuracy of your result will increase up to a point, then it will start decreasing. Because if you keep on increasing the number of step size, each step size is going to introduce some error. So that error, so long as that error is under your control, your accuracy increases. Then your accuracy goes down. Same thing happens here. Mesh is equivalent to those step size. So if you keep on increasing mesh, that is going to happen. Accuracy will be affected. So what you will do is, instead of taking 10 meshes or 20 meshes for wavelength, you are going to take, instead of 20 meshes, you are going to take 10 meshes. Now when you reduce the number of meshes, then also again your error is going to increase. If you increase it, it is going to increase. If you reduce it, it is also going to increase. So you have to find out judiciously, or you have to optimize what will be your mesh size, exact mesh size. You have to be very precise. At microwave, millimeter wave, you are not required to be very precise on choosing your mesh size. Here you are required to do that. First thing is that. Second is, okay, this I have discussed. Then next one is this terahertz is mostly used by people, those who are working using graphene. Graphene throws up some challenge. You know, terahertz size or the wavelength is 3 into 10 to the power 5 nanometers. Your monolayer thickness for a graphene, if you are taking one layer of graphene, thickness is 0.34 nanometer, which is 1.13 into 10 to the power minus 6 lambda or wavelengths. Then what you have to do is, you have to take the maximum minimum ratio of the mesh size, and that will be very large. That is one problem. Many solvers, most of the solvers, commercial solvers, they will have a restriction on this max min ratio. If you increase that, unless if you are in academic domain, there is a restriction of 1 million 1 billion meshes. Beyond that, they are not going to give you permission. If you are in industry domain, maybe you will get a permission. There you can play with this max min ratio. Again, for the large ratio, your meshing will not be proper. Meshing is going to give you problem. Then second one is, antenna problems are usually open problems. You are dealing with graphene antennas, problems are usually open problems. There you will face problem with, if it is an open problem, what you have to do is, you have to restrict it with an artificial boundary. ABC, PML, some sort of boundary condition you have to going to use. That also is going to give you problem. The reason is where you are going to put that boundary. What will be the distance from this, from the antenna? How many meshes away from the antenna you are going to put the boundary? That also you have to find out precisely. So these are certain things that you have to look into. Other thing is, at this frequency, this is almost optical frequency. Terahertz is almost optical frequency, which means you have to be very careful, because quantum effects will come in also. Physics, if you look at the physics of how it is going to behave, quantum effects also will come in. So you have to look into quantum electrodynamics also when you are dealing with this. When you are doing an analysis, you have to look into quantum electrodynamics and take that into account also if you are dealing with terahertz antenna. So there are certain things on which you should focus, or you should make your background clear, then start into working into terahertz antennas. At the lower range of the terahertz antennas, okay, you may manage. But if you go up to 1 terahertz or beyond 1 terahertz, these things are going to hamper you, or these things are going to put problems on you. Why I say this, or why I showed you that antenna with the feed that you are using, I asked my students to use this coaxial feed. Most of the students, this has become a trend. During my years, we never got this electromagnetic course. Now what we do is, most of us, you design some antennas. We take some structure, then feed it, give a plane wave feed. Usually what you are doing is, you are giving a plane wave feed and come back to your supervisor, say him that, sir, I have got a very good antenna, the bandwidth is this much, almost infinite bandwidth, UWB, everything you say, come there and say. And when you realize that, when you fabricate it, you will get a very narrow bandwidth. Reason is, you are assuming that you are feeding the antenna with a plane wave on that simulation. In fact, you are not doing that. When you are putting a coaxial probe, there it is not a plane wave. At the probe, it is not a plane wave. It is a cylindrical wave, which is, after expanding, that becomes plane wave. Here it is not a plane wave, but you are starting with your assumption that it is pure plane wave. Then you do not know what is your wave, what is your mesh size. No, none of the students usually look into how many meshes per wavelength you are taking, whether you are taking 10, whether you are taking 20, whether you are taking 15. None of the students do that. So there are certain other things. And what what is the boundary condition? None of you go for the boundary condition. Whatever is available, what is there by default, we take that. Something comes in by default in the package, you take that and do the simulation. That is what you do mostly. The students do that, and that gives you very good result theoretically. Then when you come back, fabricate it, the result is. So that is why I ask my students that you always use a coaxial probe. At least at the coaxial probe, it is plane wave. After the coaxial probe, when it comes to the antenna, it is not a plane wave. It is almost like the field that the antenna, real antenna, is getting excited. So you have to take certain precautions when you are doing simulations, and you have to be very careful if you are going to use it for the terahertz antenna or anything in terahertz. If you are dealing with terahertz, you have to be extra careful because of these reasons. One is optical, quantum effects will drop in. Second is meshing will be very important. Thank you for giving your time. If you have questions, I will be happy to question. For terahertz, no, nothing has come up yet.
The fractal antenna. So the intention is to get multiband. Where this is the first initial criteria to design one antenna. So this is the first criteria. But the second criteria is the radiation pattern
has to be different at different frequencies. So the fractal antenna, yes, these are the two things. One is you will get multiband antennas, and at different bands the radiation pattern has to be different. Then it should not be same.
No, designer's intention is to get multiband, not considering the radiation.
No. Designer has to decide these two, that at different frequencies I require different pattern and I require multiband. Only if you have a requirement for that, then go for the fractal antenna. Otherwise, don't go for the fractal antenna. No. If you require the same frequency at same pattern at different frequencies, don't go for this.
Oh, one designer, designer's mind, how the actual design which will produce that type of pattern, how it will concept, how physically someone can propose that this one will produce.
Why you are going to design? First question is why you are going to design an antenna. You have an application in your mind. Yes. That this is my application. For that application, this is my frequency, this is my radiation pattern. That you know beforehand. Before you start designing, you have those things with you. If you are designing it, if you are analyzing it, is a different thing. But if you are designing it, for that you have fixed objectives. First you have got objectives and you are trying to meet those objectives. Now if your objectives include this, that your antenna has to be multi-band, and the patterns at this point is this, at this band is this, pattern at this band is this, then you go into this. Then you choose which fractal will satisfy that. Then you design it, optimize it.
No, you are starting from for different iterations. You are starting from one geometry.
Mm-hmm.
So which geometry someone should start with which geometry? My question is, just triangular or whatever. Whatever the initial
already
geometry.
he asked me the same question he asked me. Already I have answered that. Where you are going to use, whether you are, suppose you are using only one band. What is the geometry that you are using? At zeroth iteration, what is the geometry that you are going to use? Whether you are going to use a simple dipole, where, or you are going to use a triangular monopole, or a square sort of monopole, it depends on that. It starts at that zeroth iteration.
That means purpose is to use the number of reduce the number of antennas, but if you transmit in multi-band, suppose the point-to-point communication may not be possible for other frequency bands, where the patterns are not expected.
No,
The
I
unique,
don't understand.
suppose for one band it is broadside, another band it is endfire.
Yes.
That may be the case.
Yes.
If the patterns are different for two bands.
Yes, that is what
In that case, you
said, that at
have
two
to
different
use
bands you have two different radiation patterns. Two different bands you have two different requirements. Then only you go for this. Otherwise, don't go for this.
Okay.
Like if you want a multi-band antenna, simply take a microstrip antenna. Make a E-shape antenna, you get double band antenna, two band antenna.
Please.
Sir, in all the cases, you have taken the coaxial feed, and you said that when we are using a coaxial feed.
No. I am not taking a coaxial feed in all the cases. I am saying that when we are doing a simulation, I ask my students to give a feed. There has to be a feed. Now, for all those planar antennas, ultimately you have to feed with a coaxial cable.
Yes.
Whether it is like this or whether it is like this, you require a coaxial cable, coaxial feeding. Whether it is SMA or 3.5, it depends.
You can also feed by insert feed or any other feed you can use.
Yes, insert feed, but how? You have the antenna is like this, insert feed is here. How you are going to feed here? Insert feed starts from some point. At that point, how you are going to give your throw your wave, launch your wave. At this point, you have a coaxial feed.
Yes, sir.
This microstrip ultimately goes into this antenna, but the end of the feed, one end of the microstrip line is inside the microstrip antenna. Other end, what happens at the other end?
By using SMA connector.
SMA connector. That is what I am saying. Use the SMA connector and feed there at the SMA connector instead of using that line and giving a wave port, plain wave port. Use the SMA connector. That is more accurate than using the SMA wave port. If you are putting the wave port, it is straight away you are assuming that from that point itself it is plain wave.
Mean effective gain you mentioned it.
You have different applications. You have different frequencies. In each frequency or in each band, you will have a effective gain. Take that average of that. That is what it means.
If number of bits increase, then the size of overall size of the antenna will increase.
No, that is what I showed you. Size is this. You are taking like this. Within that sphere, it remains within that sphere. The sphere that is enclosing the antenna remains fixed. When you are saying that size increases, means you are crossing that sphere. You will never cross that sphere. Yes.
Effect of the ground plane in the fractal geometry. If we vary the ground plane, so what will the effect?
That we are doing actually. I have not shown you. It is same as if you are using a microstrip antenna. Same effect. Here, look at this. Here I have not changed the ground plane, but I have changed this one. Same thing you can do with the ground plane and get the same results.
So the radiation pattern will vary, or it will remain the same if you are using a uniform ground plane. It will be reconfigurable by varying the ground plane, or
No. How you are going to get a reconfigurable antenna by using the ground plane?
means
Ground plane, if you change the ground plane, how can you make it reconfigurable? I don't understand that. But I understand this point is one point. Why you if you are making a CPW sort of feeding, why you change the ground plane? Reason is you increase the bandwidth. For increasing the bandwidth, you play with the ground plane. But it is you don't play with the ground plane to make the antenna reconfigurable. If you are making the antenna reconfigurable, means you have to change the antenna itself, not the ground. Reconfigurability does not come with ground.
The last couple of queries, please. Hello?
Yeah.
So,
Yes, I showed you one example. Complementary, I showed you.
sir, is there any utilization of negative gain in antennas? Because in some of the research paper of KJ Binoy, he has represented the antenna with negative gain for all the bands.
Yes.
What is
I
the
prefer
reason?
not to answer this one. I will leave it to KJ Vinay. He's coming.
Okay.
So discuss it with KJ Vinay. He will be more.
Because that is most important
He is
part.
the authority on that.
Okay, sir.
You ask him.
Okay, sir.
Yes.
Last query, please. Increase the meshing, errors will increase. If we can reduce the meshing, errors
Also
will
errors.
increase.
Yes.
So how we can take care of meshing? What should we do for that?
There are optimization methods for deciding what will be the meshing. So first you have to read that. That is what I said. That when you do electromagnetic simulation without understanding you do not know what is FEM, you do not know what is MOM, you do not know how the meshing is done, and you start using the optimization method. There is the problem. First you understand what is meshing, how you are doing the meshing. Read those things are available in literature. Read that, then you do this. Okay, last question.
Okay. So this will be the last query for the day.
Sir, the problem that you told that happens in case when we are giving a feed, we do not incorporate anything which could give us an intuition of what would go wrong when we do not have a planar effect. Can we do anything at the simulation level that would incorporate possibly that effect so that we can rectify that at the time of simulation?
That is what I said. That use the proper feed. In the simulation, design the feed also, simulate the feed also along with the antenna.
But sir, what if the feed is coplanar?
This is a coplanar feed.
Yes, sir.
Okay. This side is the antenna.
Right, sir.
What happens here? Here you have to use a feed, coaxial feed. So you start from that. Here you put the feed itself and start from that. That is what I am saying. Use the SMA. You are using SMA feed usually. Design the SMA or coaxial feed. Use that here. Center conductor will be here. This is actually that SMA. Center conductor will be here. Flange will be connected to the ground.
Okay, thank you, sir.
So start with that. Right.
That was a beautiful illustration on fractal antennas with experimental work supported by the theory. And Professor Mishra has taken us into a new world of antennas today. He also mentioned some of the requirements when one goes to the application of terahertz antennas. I am sure the discussions are quite interesting, and there are many more perhaps coming into the minds of the delegates. They may continue their discussions with the author in the off time. I'm very sorry that we have to cut down some of these queries time, because the session was supposed to end at 7 o'clock and now it is 8:20. But I appreciate your patience. You have been interacting with the speaker quite proficiently and efficiently. And I also thank the organizers for giving this opportunity to be associated with you in this capacity. Thank you, Professor.